Good morning. Welcome to attend our briefing. So today we're talking about JDD, in-depth mining of Java Deserialization Gadget chains by bottom-up gadget search and Dataflow-aided payload construction. So myself is Yingzhi Cao. I'm associate professor at Johns Hopkins University. I'm also the technical director of Johns Hopkins University Information Security Institute. So my research is about cybersecurity and privacy issues in the web, smartphones, machine learning, using different type of program analysis techniques. Together with me, we have Bofei.
Hi, I'm Bofei Chen. I'm a PhD student at Fudan University from the Success Lab. And my research interest focuses on the program and size, vulnerability detection, and exploitation.
And we have our collaborators include Dr. Lei Zhang from Fudan University and Xin You, he's a master student, and also Dr. Yuan Zheng and Dr. Min Yang, both from Fudan University. So this is our agenda. So you may want to ask, so our title is very long. What is Java deserialization vulnerability? So to start that, we need to understand what is Java serialization and Java deserialization. So those are the inverse process of each other. So basically, as you can see it here, we have a Java object. It may have several fields like A and B. And in order for the Java object to be communicated from one end to another, for example, like a server to a client, so the Java object needs to be serialized into a stream of bytes. This will be communicated through some channels, for example, like HTTP or some TCP channels, and then a stream of bytes are going to be deserialized into the object itself, contains exactly the same field A and field B. So this is called Java serialization and deserialization. So there's different type of application scenarios like communications, data exchange, and everything like caching. So it's widely used in the field. Then that is what we call Java deserialization vulnerability. So basically, in a very short sentence, so Java deserialization vulnerability is that by carefully manipulating the types and the values of serialized data, an attacker can control the serialization process and therefore can lead to some consequences like remote code execution or some other consequences. So basically, it's two steps. First is that attacker can control the deserialization process, and second, that it can achieve some consequences like remote code execution. So you may ask, how popular is Java deserialization vulnerability? So it's a very high impact risk. So in 2017, so it's still called like insecure deserializations by the OWASP top 10. So it's ranked number 7. And then in 2021, actually they changed the name. It's called software and data integrity failures. It's still like among the top 10 of the OWASP. So it's a very high impact risk. And you probably heard about the very famous log4j vulnerability, the log4share that CVE 2021 44228. So that impact 84,000 machines within 2 hours of its release. So it's very powerful. Probably already heard from the news in the before. So it's a very high impact a risk. And also, the deserialization itself is really widely used. This is a built-in features in Java, and it's integrated across different type of frameworks. For example, RMI, HTTP sessions, and therefore to completely avoid or replace this Java deserialization itself is very challenging, and we have to face the existence of Java deserialization. So more specifically, I know we were still too abstract so far. So let's take a look at Java deserialization vulnerability. It's a proof of concept, a very simple Java deserialization vulnerability. So the code we have here have two parts. So first is client side. As you can see it here, we have the object. So basically, we could have the get request message, and then it's going to a serialized object through the Hyphen protocol and with this line 5 at serialized data, and then it's going to be written into a socket. So this is the socket, and then it's going to write this to the socket. And then after that, come to the server side. So what it does is going to read from the socket. So this is the line 3 and line 4 is the socket, and line 5 is you get this hasten to input, and then we use this very important like a function called read object. So it's basically read the object that being like a serialized and deserialized this into an object. So then those constructed objects can be used in other business logic, for example, like a message handling, order processing. So anything that being sent from the client side to the server side are going to be involved in this object. But there's a problem. So what the problem is that this is an object. So therefore, it may contain some like function, some method as well. And then during this process, what attacker can do is that it can carefully craft a hash map. For example, here is hash map instance. So, and if you have a hash map instance in the object, and then the read object, what we can imagine is that it's going to recreate the hash map and then put like information of the object inside the hash map. And then you can see it here on the code we showed is a like a map that equals to new hash map that is being part of the like read object code. And then it's going to have a recursive call. It's going to do another read object and then put that object in as part of this hash map. Then that's come the problem is that when you do the put, one of the like a function call is going to be like executed is this key dot equal, because you need to find out like what key about this hash map is. And then this key dot equals could be a like a polymorphic like a function call. So it's not the direct equal, but when you do the inheritance, it could be a equal of another function. And therefore, the attacker can utilize this polymorphism in this Java object and then introduce the malicious consequence. More specifically, so here is we show what attacker could do. So you can see it here. We have this hash map, and inside the hash map we have this key dot equal, and then if this key actually equals to this evil example, so in this evil example class, it has a like equals like a method which is inherited from the other method, and then inside of this, and it can do is that it can call like a runtime dot get runtime, and then do execute. In the execute, it's going to execute this o.cmd, so which is basically part of this evil example. It have another like attribute, and then it can like execute and achieve the consequence of like a remote execution. So you can see we want to show an example of Java deserialization vulnerability. And then the question is, how are we going to detect and exploit a Java deserialization vulnerability? So there are two important concepts in order to exploit a Java deserialization vulnerability, so which are a like injection object and a guarded chain. So basically, an injection object is a serialized object. We see it before, like between the client and server, going to serialize this object, so injection object. And then what the guarded chain means is basically is something that borrowed from, like, for example, rich-oriented programming, the C. So it utilizes a polymorphism of like a Java method so that it can invoke a series of security-sensitive methods that are capable of, for example, like executing malicious code during this deserialization process. So as we can see it before in our motivating example, that the guarded chain looks like we have the hash map dot put, and then it will call this evil example dot equal, and then it will call like a runtime dot execute C. So basically that leads to a chain that eventually execute the like a malicious code. So this is a problem, and the issue is that it's very hard to defend against this like Java deserialization vulnerability. The reason is that in previous like approach or previous work, what they usually do is that they will set up a like black or white list to restrict some classes. For example, like evil like example that we showed before, that can be deserialized so that it can truncate the guarded chain. Basically, it does not allow the code that we have shown that it can go through the like evil example and goes to the runtime.execute. But the problem is that there are many different options difference. So it could be the evil example. It could be another like evil example too. So that also leads to the final like a gadget like a sync, which is the like runtime.xec. So as you can see it here, so what we do is that we started like a web logic. So basically, it's a like framework contains these like Java deserialization like vulnerabilities, and we try to like put all the CVEs related to Java deserialization vulnerabilities in the graph. And you can see that like once we have a like for example, this CVE and goes to another CVE means that they share most of the gadget, but just a few differences, but it can still lead to the vulnerability. You can see that they have a lot of like sharing of those like gadgets around like each other. So that becomes a like a bigger problem in terms of defending, also in terms of like detecting, because in terms of detection, we need ways to find all these possibilities to detect this vulnerability. So we show an example here. So basically, you can see here is a like a code that a part of the CVE 2020 2883. So you can see it here. The original vulnerability goes through abstract extractors dot compare, and then eventually it leads to method dot invoke. But in our case, that we found, oh, it can like bypass this specific like a gadget chain. Basically, is a like a blacklist. It does not allow, for example, certain like abstract structure, but we can still find this extractor comparator dot compare, and it can bypass this blacklist, can still lead to the same like a severe consequence. So basically, as we can see, that the threat is persistent. So it's very hard to defend against this type of Java deserialization vulnerability, and also it's hard to like detect this vulnerability. So next, I'll turn over to Wofei, and she will discuss like how we're going to detect like those Java deserialization vulnerability chains using our like a JDD tool.
Now, next, let's discuss why it is so hard to build a foolproof defense that catches all possible gadget chains. It mainly comes down to two major and unresolved challenges. To illustrate, I will walk you through a real-world and zero-day gadget chain uncovered by JDD. The gadget starts from the fragment 1, where the put method of a hashing map object is invoked on deserialization, and normally this method is used to restore the key value pairs from the serialized date and back them to the type field of the reconstructed hashing map instance. And if the two pairs share the same hash value, the program can be introduced to invoke the equals method of the variable key. And since the key's declared type is the object, it can be assigned to any types of Java object by the attacker and source controlling the subsequent exclusion. For example, if we place two simple entry objects into the hash map's type value and make sure that they share the same hash value, the program can be introduced to jump from the fragment 1 and to the fragment 2. And following, we simply name the two instances as the S1 and S2. Now we'll continue to follow the attack path. At line 16, the program will pass the key field of S1 and the S2 into the EQ method and invoke the equals method of the key field in the S1. So if we further assign the key field as an extreme for FSB object, we can further introduce the program to jump to the fragment 3 here. And then at the line 26, the program will invoke the toString method of the key field of SS2. So if we assign this key field as a JSON object, the program will be further introduced to jump to the fragment 4. And now, let's go back and consider how to make the S1 and S2 have the same hash value. Based on the hash code method of the simple entry, we can know that we need to store the same string for FSB and the JSON object instance into the key and value fields of both S1 and S2, but in reverse order, just like this. And similarly, we can control the program's execution to reach the fragment 7 by manipulating the types and values of these fields. And in fragment 7, the program can invoke unsafe driver reflection and then be introduced to jump to the fragment 8. And if we can craft the relevant fields to satisfy the required conditions, just like in this conditional branch, for example, the active retry count should be less than the active retry max, and we can finally launch a command injection attack as shown in line 64. However, it's very difficult to detect such real-world gadget chains in a limited time due to the static path explosion. Just as shown in this picture, it's easier to encounter many dynamic misinvocations during the search, and these dynamic invocations can have many implementations that the attacker can control. For example, in this application, the toString method of object can have the 3,129 implementations. So, if we use the existing detection approaches that employs a top-down static analysis to extensively search gadgets from a source to a sink for all potential paths, the candidate search paths could grow exponentially with the search length. And secondly, if it's also very difficult to generate an injection object to trigger this chain. As shown in the picture, the injection object usually has complex, parallel, and embedded object structure, as well as the field-related constraints and dependencies. Thus, it's very difficult and almost impossible for random mutation to generate a useful payload to validate the chain's exploitability. So, how do we address these two challenges? First, we address the path explosion challenge for a fragment-based summary and a bottom-up search approach. One of our key observations here is that a bottom-up search can find gadget fragments that can be reused by different top-level gadgets in the gadget chain, and thus reducing the search complexity from the exponential to polynomial. And now, let's discuss an important question. Why do we need to perform fragment-based summary? As we know, one common approach to address the problem of path explosion in static analysis is to use the state propagation. And this method encounts the path information onto nodes rather than preciously calculating all possible exclusion paths, thus triggering space for time. However, because a chain can have many gadgets and the dynamic method calls introduce a significant number of program state branch, if we were to track all the states precisely, we would encounter the issue of state explosion. So, to avoid both path explosion and the state explosion, we have designed a hybrid analysis approach. Specifically, within the fragments, we mainly retain state information, and between the fragments, we retain path information. Specifically, to prevent the state explosion, we break the complete gadget chain into smaller fragments using the dynamic method call, and thus reducing the number of path nodes that need to analyze. And at the same time, we partially retain state mapping to further avoid the state exploitation. We only summarizing the chain behavior between the last and the first method, and the link conditions as well as exploitation conditions for the last gadget. That means the sink method. And we then search for the completed chains that link source to sink based on the fragment mapping to perform a lightweight path-sensitive analysis. And moreover, in the fragment training process, we adapt a bottom-up search approach. This is because we can infer the precise linking requirements based on the recorded exploitation conditions for sinks and the reverse tent relationships, thus enabling on-demand state merging and path analysis. and this approach further reduces the redundant and duplicate and size. And secondly, we observed that different injection objects, for example, their fields, are connected for data flows. And thus, we can use static time and size to conduct data flow dependencies between possible injection objects fields and use them to further guide the dynamic fuzzing to generate exploitable objects. So, based on these ideas, we developed an automated Java Deserialization Gadget trend detection tool named JDD. The architecture of JDD consists of two main stages. In stage 1, JDD detects possible gadget chains, and then in stage 2, JDD generates injection objects to verify these chains' exploitability. Now, let's walk through the specific workflow of the JDD. For this motivating example, we first identify the deserialization entry method as a put method of the hash map. And in step 2, JD will use the static time and size to detect useful gadget fragments that could be chained together to construct the gadget chain from source. For example, JD starts from the put method of hash map until the next dynamic invocation, the equals method, and treats the calls in between as a fragment. And for each fragment, JD will perform data flow analysis to record the time mapping relationships between the last method and the first method. We named it as the bottom-up time behavior. And secondly, JDD will also record the conditions on how to link this fragment. And this condition will ensure the control flow reachability of the next fragment. And thirdly, for the sync fragment, JD will also record the specific exploit conditions for sync gadget. For example, which parameters must be tainted, or that means must be controllable by the attacker when invoked. And then JD searches for the subsequent gadget fragments using all unsearched implementations of the dynamic method as a new source. And finally, we can obtain 3 categories of fragments and begin bottom-up training. In step 3, we train the gadget fragments from sync to source. The core idea here is that a bottom-up search a top-down search cannot determine in advance whether a sync is ultimately reachable, and often resulting in a large number of redundant and ineffective search. But in constraint, a bottom-down approach enables us to use the exploit conditions in combination with the reverse taint mapping to accurately compute the taint requirements for the pre-linkable fragments. And additionally, by applying the link condition, we ensure that control flow reachability between fragments is preserved. And together, these constraints allow for a more focused and efficient fragment composition process, significantly reducing the overall search complexity. And next, in step 4, JDD will follow the call sequence in the gadget chain to construct the data flow dependencies between the possible injection object fields. And JDD mainly focuses on the 3 categories of constraints. The first type involves the class hierarchical relationships between objects and their fields instance. These constraints are used to guide the generation of the initial set, ensuring the dynamic method invocation correctly jumps to the accepted next fragments. And to identify these constraints, first, JD will perform a taint analysis to identify which fields in the fragment are linked to the next fragment. For example, in this example, the table field of the hash map instance is used to link the fragment 2, and then determine the type of the field of the elements in the field based on the head method of the next fragment. For example, we can, based on the next gadget, the equals method of the simple entry to determine that the table field stores instance of the simple entry type. And in addition, JDD will extract and solve field-related constraints as well as field dependencies constraints to ensure the smooth invocation of methods within a gadget, within a fragment. And these are very critical for understanding how to craft specific fields to achieve an exploit. And note that we also extract implicit constraints to make sure the program exclusion would not trigger an exception. For example, a field could not be none when it enforces some methods, and another example is forced typecasting, which requires the field should be an instance of a specific type. And after extracting all these constructions, JDD will use a no-fault structure termed IOCD to model these constraints. And there are two main sub-steps. In step 1, JDD will treat the initialized object content in a gadget chain as the class node. Each class node stores the following information: the class name and the related field nodes, which represent the fields that may be used during the deserialization. And the field node, on the other hand, stores the relevant constraints information for this field. And in addition, JDD will identify the fields that store the attack payload, as well as the specific constraints among these fields that are related to the attack payload construction. And in step 2, based on the structural constraints, the class nodes are interconnected through the field nodes using the directed edges, thereby indicating the hierarchical relationships between the instance and between this instance. And next, in step 5, JDD will use the IOCD to enhance or directed fuzzing to generate exploit injection objects. The high idea is that, given a gadget chain, JDD will first generate a high quality initial seed with a suitable structure based on an IOCD. And then JDD will use the IOCD to select appropriate fields for mutation and reduce the uncertain mutation space through the constraints information, and implement a dependence-aware seed mutation strategy to maintain the validity of the overall structure at the time of mutation. The process of generating the injection object mainly consists of 4 key steps. Firstly, JDD will analyze the parameterless Java instance objects based on the class node, and then establish the class hierarchy among these instances using the directed edges. And third, JDD will select fields related to attack payload constructions. And lastly, JDD will extract necessary constraints that can be determined in the static analysis, and use a constraint solver to generate appropriate values, and which are then assigned to the corresponding fields. And then we will inject the generated object into the target deserialization method and check whether it successfully follows the gadget chain to reach the sync gadget and trigger the expected exploit behavior. And if it does, the chain is marked as exploitable. Otherwise, JDD will apply these 3 mutation strategies to address the object accordingly. And finally, we will show how these insights fit into real-world evaluations and reveal new findings. First, we evaluate and compare the effectiveness of JDD on well-known benchmark. The results show that JDD significantly outperforms all out-of-the-state tools and detect 19 unknown gadget chains that are not detected by the baselines. And in addition, JDD identified 127 zero-day gadget chains in 6 popular Java applications and notified affected the developers to help them resolve these issues. And this proves the value and impact of JDD in the real world. And below, we show two interesting exploitable trends detected by JDD in the benchmark. The both trends in the first case rely on the popular library Groovy. But the gadget chain with different construction methods may have different attack scope. The non-chain can only attack protocols that support the dynamic PRO6 feature, whereas the unknown chain detected by JDD does not have this limitation, expand the scope of attack. For example, it can be used to attack Hidden, which is also widely used in distributed system microservice architectures and so on. And the second unknown chain can be used to attack a deserialization protocol outside the scope of JDD's predefined detection rulers, which the Apache Fury, which is a newly appeared deserialization protocol. And this demonstrates the extensibility of the JDD. And next, we demonstrate how replacing certain fragments in real-world zero-day gadget chain detected by JDD can broaden or change their attack surface. As shown in this picture, this gadget chain, which relies slowly on the JDK and the popular library FastJSON2, can exploit many widely used Java applications like Sofa and Solid. However, it cannot exploit Morton, as Morton does not include FastJSON by default. But we found that by replacing the fragments 4A to 7D from case 1 with the fragment 4A to 8 from case 2, we can generate new gadget chains capable of exploiting the Morton. And this is possible because the case 2 relies on Jackson, a library included by default in the Morton. Next, just as we discussed earlier, geo-deserialization vulnerabilities are difficult to fully defend, and can often be exploited by attackers through the replacement of certain gadget fragments to construct new exploitable chains. So to help developers identify potential bypass, we present some notable gadget fragments. For instance, we have found alternative fragments that can replace the second fragment from the deserialization entry point to the comparator compare. And replacing this fragment not only bypass the certain application level blacklist, but also extend the range of the exploitation protocols from the JDK to such as Hidden. And other examples include alternative fragments for triggering the hash occlusion. And as well as the chains leading to two-string invocation. Or the fragments that bridge unsafe reflection with the final exclusion effects. And these fragments are also critical components in some of the zero-day gadget chains we have discovered. And due to time constraints, we want to go into the details of these fragments in this session. And finally, let's make a conclusion. In this session, we introduced a fragment-based summary and a bottom-up gadget chain search approach that effectively address the challenges of static path explosion. And we introduced an automatic detection tool, JDD. And JDD also uses a technique fragment that leverages a lightweight static analysis engine to guide the directed fuzzing, thereby enhancing the precision and efficient in the vulnerability verification. And lastly, we also shared some several-day exploitable gadget chains and fragments discovered by JDD. And we appreciate your time and interest in our research. Thank you for your coming. And if you have any questions.
Welcome, like any questions? So theoretically, like any sync fragment can be used in the our application, so it's extensible. So currently, you can see that we already used some command injection. That is the most vulnerable gadget we have found. We also use, like you said, some arbitrary file read, arbitrary file save. So I think current implementation only look at those three, right? The command injection, file read, and file write. Do we have anything else? Yeah, I think basically just like what I said. So most of them are extensible, but we do right now is mostly command injection and some third-party a library like load and also JNI execution as well. You're welcome. Any other questions? So yeah, I would like to stress that our JDD is open source. So you're free to use our tools. We have two parts. One is the static analysis part. Another is the dynamic directed fuzzing part. So yeah, you're free to use our tool after this talk. Okay, if no more questions, I think that's it. Thank you for attending the talk.